All right, my friends, cool. Let's settle in. All right, please, and I ask that you do nothing, even if you're not participating. You stop producing, you crazy consumer capitalist. Stop it. Just let it all go for 2 minutes. And just notice what it's like to just be here doing nothing. Find your brain picking up tasks or worries, just drop it. And repeat this process. Here's your raw experience at this moment. Where's the center of that experience? See if you can briefly, just an instant look. For the one who's experiencing all of this. And then come back to producing and doing, calculusing. Jeez, my glasses are super filthy. Sorry, guys. I'm so punchy at this time of the semester. I was just like, man, I feel good, but I feel pretty casual. Do y'all have any questions? Probably not at this point, right? The web work, that was due yesterday, we're good. I've got one more web work for you. It's not a very big one. And then I'll have a bunch of final exam review stuff that I will get out to you. We don't meet on Friday, right? Does everybody know that? There's no class at all on Friday, but I would like to have final exam review stuff to you by Wednesday. That's my goal, because I want you to have at least more than a week. And then we're gonna have a couple more days of pushing forward the current material. And then I expect next Friday, at a minimum, to just be like come and work day, right? I will stop, I would like to stop talking on Monday about new things. That's my goal, so we'll shoot for that next Monday. All right, let's push this forward. Let's review a process here. I've got a function. Am I recording? Yeah. Yes, thank you. Wonderful. Got a function. La la la. And I want to find this area underneath here. I want it precisely. So you're going to see the same ideas repeated. These same themes are going to pop up, but we're going to push it further today, like literally and figuratively. We're going to do that. So I want that area, A. So what I do is I cut this interval, A to B, into n pieces. So step one is to cut the closed interval A to B into, and so far I've been saying even pieces, equal pieces, but not anymore. Today's like the full-blown exposition of all of this into n pieces. And we do this by choosing is x sub 0, which is going to be a, and then I'm going to pick a point to the right of that, x sub 1. So let me kind of do this. Here's x naught, x sub 0, and then I'm going to pick a point x sub 1, which is to the right, and I'm going to pick a point x sub 2, which is to the right of that. I'm deliberately making those not look equal. So they don't have to be equal, these cuts that I'm making. And then less than x sub 3, blah, blah, blah. And I go all the way out. Here's the second to last one. And then the last one is b, which we'll just denote as x sub n. This is called a partition of the closed interval. So this is a partition of closed interval a to b. Just a selection of points in the interval. Once I've chosen those points, they produce intervals. So the little subintervals are the spaces between the points. Let's put that up. 2. These points produce subintervals. In fact, n subintervals. But the subintervals are going to look like this. Each subintervals of width, let's just get the width out here, delta x sub I equal to x sub I minus x sub I minus 1. So there's going to be a lot of notation, and please try to follow. If it starts, yes, this is what I want.
Is that delta sub xi or delta x sub I?
Delta x sub I.
Okay.
So you could literally think of that sub I as acting on the whole thing there, if you want, Alex, but yeah. Okay. So here's delta x sub 1. Here's delta x2. Here's delta x sub n. Notice that those will always be positive because I'm assuming that these points are moving to the right. So this x sub I is always to, here, let's draw a little picture with this. Here's xi. Here's xi minus 1. And this distance right here is the right endpoint minus the left endpoint. Yeah, okay. So we've got these new subintervals. Above each one of these subintervals, next step, 3. In each subinterval, choose a point. Choose a representative point, and I've been using that word deliberately so that this isn't the first time you've heard this, a representative point. What do I mean by this? Remember how we were either using the right endpoint or the left endpoint? We'd get that upper sum and then that lower sum, or the right-hand sum and left-hand sum. You don't have to just pick the endpoints. In fact, I think Kitra, early on in this, said, what if we use the point in the middle? I think you said that. And you can do that. Guess what? You can use any freaking point you want in each subinterval. So choose a representative point C sub I. So drawing the picture out here, let's take a look at, here's just an arbitrary, here's xi minus 1. We're zooming in on just some section in the middle there. This is a zoom in, and I'm going to pick C sub I inside there. Let me give you a nice solid example here. Let's suppose n equals 4. So just so you can follow along, because this is all very abstract, and for some people this works, and not so much for others. So let's say here's A, here's B, and here's x1, here's x2, here's x3, and then this must be x4 out here. And this is x sub 0 right here. So far this is what I've got. I'm going to pick C sub 1 there. I'm going to pick C sub 2. Look, it's really weird and not at all in some sort of rhythm with this. I'm going to let x sub 3 be the freaking right endpoint here. Why not? So there's C3. It's literally the right endpoint, and then here's C4. It doesn't matter, as long as they come out of that interval, you're good to go. Okay, so, ooh, this is wicked. Got my lazy boy lounger all set up. That's good. So, any questions on this? I feel like a Muppet, like a Muppet, like teaching this. Yeah, what was that?
I was gonna say, I don't know where this is going, but I'm interested.
Ooh,
I don't know why we pick random points with C's.
cool, I like that. That's exciting, that you're interested. Nice. A question?
So you're finding, just a clarifying question, so once you find points like x1, x2, x3, you're finding points within that point?
Yes, ma'am.
Okay.
Exactly. Perfect. And so what I'm going to do next is use the value of the function of these representatives to determine the height of my rectangle. Because I'm going to put rectangles above each one of these, and I have to figure out how high they are. So go to the value of f at the representative to determine your height. And that's step 4. Above each subinterval, construct a rectangle of height f at that representative, and the width is going to be delta x sub I. So another picture. More pictures the better. Here is x sub I minus 1. Here is x sub I. Here's my function. Here's c sub I. And I go up that high, however high that tells me to go, and I make my rectangle that height. And I'm going to do that for each one of these subintervals. So maybe if I come back to this picture, I don't know if you ever noticed, but all my arbitrary functions are the exact same function as like I established this long ago, that it was going to look like x cubed, and I just roll with it. So for this one here, there's the height, and you use the edges of the interval as the sides of, so here's height C2, so that's going to be the height there. Come here, that's the height for that one. And this one is that height. So after doing that process in that picture, that's what it would look like. Notice how all the rectangles are different widths and different heights, and it's kind of all over the place. Not at all uniform like what we've been doing. We're going to add up the areas of those rectangles, and that's going to be an approximation to the area. So step 5 is add up the area of these rectangles. And what that's going to look like, let's write it without notation first. So we have height. So this will be the first one, C1, times delta x1. So this is height times base, plus the height at C2 times the width of that subinterval. And then I do this all the way across to f at C sub n delta x sub n. Now I'm going to kill myself on this. Get this up. So this is just note, this isn't part of the notation. That's just noting that this is the height times the base. We cool with that? Does that sound right? All right, good. Let's use notation, i.e. in beautiful sum notation, sum from I equals 1. Notice how the indent, what is changing from different pieces of the sum? Something goes 1, then 2, then 3, on up to n. So this is the thing that ticks off the part of the sum that I have. And here I've got f of c sub I delta x sub I. This is a Riemann sum. And I introduced that Friday. So this is a Riemann sum. Riemann sums are approximations to that area. You can think of it that way. It's It's an arbitrary thing. We want perfection. We want the truth. This is only an approximation. Unless that function looks like this, a rectangle to begin with, this is only approximate. But if it's a rectangle, I'm good to go. But like in life, you know, I mean, if it was a rectangle, what the fuck am I doing this for? I just find the area, right? So it's going to be something more like this, where you can see that I'm under and over, and gosh, I don't know how those add up. I don't know how the final answer works out. So what I'm going to do is let the number of rectangles go to infinity. So if the function f is continuous, and this is a little strong. It could be looser. We can actually have some discontinuities way beyond the scope of this class. If f is continuous on the closed interval, in other words, no jumps, no holes, no breaks, it doesn't shoot off to infinity, then limit as n goes to infinity of this sum. Now this is some good shit to write down. Like when you start writing stuff like this, it looks like you know what you're doing, right? And it's like you show this and people are like, college math. That looks like college math. Because I don't know what that means, but you do. So another way to say this, notice here, so let's take a look here. Note that the width of the rectangles goes to 0 as the number of rectangles goes to infinity. And they're just shrinking, that base is shrinking. You're cutting that thing into more and more pieces, so they have to be smaller and smaller. So this whole process is called integration. The minute I put this limit in front, I've now created something called a definite integral. So there's a symbol for this whole process. So this is a definite integral. An integral is a process, just like a derivative is a process. The derivative's a freaking limit of two differences. A definite integral is a limit of an infinite sum, or it's a limit of a sum. It's an infinite sum. So we have notation for this. If that thing exists, if that limit, I can take it, it doesn't blow to infinity, it doesn't bounce around, it do all sorts of weird shit. If that limit exists, then we write that this thing here is equal to, the sum sign becomes that simple. It's like an S stretched out. It's called an integral sign. Integral sign. So it's a stretched out S. It deliberately looks like an S because integrals are sums. I started at A, I went to B, so that's the X range. That's the interval on which I'm doing this. This just becomes f of x, and the delta x becomes dx. You've seen that before, right? But now, look at this. A lot of people see this, and maybe if you did this in high school, you just kind of learned the mechanics of it, right? You know, I know the power rule, and I can totally do those. But did you know that this is what it is? Because this is, a lot of people know that, and they've seen that. But they don't know that it's this. It represents steps 1 through 5. That's pretty heavy. So this part here is called the differential. This is all notation. It's the differential, and it used to indicate the variable. To indicate the variable, and to also frame off the function. You can think of this as like the capital of a sentence, and this is the period, and this is the stuff that's happening in the sentence inside here. So this is used to indicate the variable and to cap off the integrand. And what is the integrand? The integrand is this thing. So it's the thing, it's the function you're finding the area under. Integrand. And then this A is called the lower limit. And the B is called the upper limit, not shockingly. And altogether, this is called a definite integral. And I would read this, if I were to read that on a page, I would say, this is, I wouldn't probably say the definite, I would just say it's the integral of f of x from a to b. The integral of f, whatever that expression is, from a to b. So all these things are ways to say that thing, which is a way to say this whole process. Good news, you don't have to do this process. Remember when I did x squared and we did it, I cut the x squared function. We found the area under x squared from 0 to 1. And it was 1/3, yeah, it was x squared. And we did that by basically doing this whole process, cutting it up into arbitrary rectangles, letting the limit go to infinity. The good news is, this is as simple as differentiation. Because imagine, right, the beginning of this class where I was like, you know, when you take derivatives in this class, well, you're gonna do this every freaking time. You might have quit. But it turns out that this was just a move of an exponent. It was just a rule. And moving that exponent did this. Same thing's going to happen here. Moving exponents is going to do this. How can that be? But it is. So let's talk about that part of it, because this is where the fun starts now. All right, so you've paid dearly. It takes a while to get to this point, so good job. Thank you for your attention. Let me refresh your memory about one other thing. Recall, because I want to make a connection here. When we had a velocity curve, we had velocity and we had some velocity curve, and then we had time here. And we wanted to find the distance, the displacement. So find total displacement. And this was A, and this was B, and this is your v of t function right here. What were some ways we did that? There's two ways. What was one of them?
We found the area, we got the upper and lower averaged it.
Beautiful.
Those rectangles.
Yeah, beautiful. So that was the painful way, right? We just worked with triangles and rectangles, but we found the area under this curve, and that represented the displacement. If it was negative, it was just, we were moving back, it was negative displacement. But the total displacement, in other words, my position at B minus my position at A. So this is total displacement. This is, let me write that out. This is position at B, time B. And this is position at time A. Was equal to the area under this curve, which we now know can be notated like this, is the integral from A to B of the velocity function dt. Notice I got a t there because time is my variable. So this is just letting your reader know what the variable is. It's just notation. So this difference was that. But what's another relationship between velocity and position?
Velocity is the derivative of position.
Velocity is the derivative of position. So this is the tie right here. But also, thank you, Nina, position, ddt of position is equal to velocity. So position equals the antiderivative. Remember we did this too. of v of t. So I'm writing that relationship backwards. I need to find the function s of t whose velocity, whose derivative is this velocity function. So this s of t, let's write this out, is equal to a function whose derivative is v of t. So instead of finding the area, let me say this again. Now, this is the big deal. Instead of finding that area by like doing this whole thing, if you got triangles and rectangles, you're in good shape, but as soon as it's curvy, you're out of luck. You've got to Riemann sum it, then take limits. So, shit, let's see here.
Can you plug in numbers? Does that help?
Yeah, no, I'm trying to think. I was about to go somewhere like that felt really good, and then I started babbling down another road. Let me think where I was going to go with that. Oh, okay. Yeah. Okay. I'll get some numbers out here soon, Alex. I know it'll help. I know it's going to feel good. To find this, just find an s of t such that the derivative of s of t is the velocity function, and evaluate s of b minus s of a. Now I'm going to do a solid example. Suppose my velocity function is t cubed. I'll just go real chill for right now. Oh, no.
You mean 3t squared?
Oh, no. Oh, I got something even better. Sometimes I like coming to class because I don't quite know what's going to happen. And sometimes that's exciting when something happens I didn't really see. So suppose v of t is this. So here's my velocity function. Parabola, the old parabola. And there's 1. So here's my time unit, that's velocity. I don't know, let's come up with some shit. Seconds. And then this is meters per second, sure. So I've got a particle whose velocity starts at 0 and ends up at 1 meter per second, and it's accelerating, right? It's starting out pretty slow, it starts out dead, right? Just not even moving, and it starts getting faster and faster. Think about this is the velocity, right? So it's increasing in speed, it's accelerating. I want that area under there to be my total displacement. Now we already know what that area is, because that was the first thing I did. That area is 1/3. Does that sound familiar? I hope so. I hope that sounds familiar. But let's do it with this idea up here. So can somebody give me a function whose derivative is t squared? What power does t have to be so that if I take the derivative of this, I get that?
3.
Beautiful.
1/3.
1/3 in front. Yeah? So the derivative of this, power rule, 3 comes out in front, is that.
Plus c.
And plus, we can put a plus. We can put whatever we want here, absolutely. That's a good observation, because the derivative of that c just goes away, so it could be anything like this. Hell, let's leave the plus c on, I like it. So according to this idea here, the total displacement, so here, let's just take a little note here. We took an antiderivative. And if you're like, antiderivative, what? I still don't get it. It just means the derivative actually happened in this direction, and I'm just pretending it was a backwards thing. So the total displacement, this total displacement is equal to this integral from a to b of my velocity function, t squared dt. This should be 0 to 1, excuse me, because I actually know those. And this is going to equal s at 1 minus s at 0. That's my position function. And that is equal to what? 1/3 times 1? 1/3, just like we knew. So notice the antiderivative gave us the same answer as the Riemann sum with infinitely many rectangles going to infinity and all this shit. Same answer both ways, way less pain with antiderivatives. All right, so this what just happened is an example of the fundamental theorem of calculus part 1. So let's write that out. The fundamental theorem, it only takes 3 or 4 months to get to it. Theorem of calculus says the following, that the integral from a to b of a function can be computed with the following difference, where this f is any antiderivative of little f, where big F is any antiderivative of little f. That's the fundamental theorem of calculus right there. It links the integration process with derivatives. So now we've tied together first portion of the class with what we're talking about now. And this is part 1. I should have put that there. We'll get to part 2. Let's spend a couple days on part 1, because this is really what I want you to be able to do when you walk out of here. So first thing is we need a table of antiderivatives and some rules. So let's get some basic antiderivatives. New table. You can use a derivative table, but it's nice to have one written in this form, this way, just specialized for us. So here's my function. And here's the antiderivative. And antiderivative. They all can be adjusted with a plus c. So we're not going to write that on. So the function x to the nth power. So think about how you differentiate it. Remember, derivatives were like, bring the exponent out front and decrease by 1. So we want to do that in reverse. So what we do is we add 1 to the exponent and divide by the new exponent. And this is good as long as n isn't what? No, it works for that actually.
1.
It would. Actually, I got to think about what. I think it does work for, but -1. -1 would be super bad. But you were thinking of division by 0, I think. So as long as this isn't -1, we're good to go. Oh, what happens if it is -1? Well, that means x looks like this, and hell, let's just get it out here. Whose derivative is 1 over x? Good old log, right? So now this is all powers of x are handled with these two things. Let's get a couple more up here. So that's 1, that's 2. If you look in normal tables, they do put a little plus c on. People lose like points because they don't put plus c on shit. I'm not going to be brutal about that until you get to Calc 2. And some of you, then I'll be tormenting you with plus c requirements. So let's do some trig stuff. Oh, here's an easy one. Whose derivative is cosine? Sine. Beautiful. Whose derivative is sine?
Negative cosine.
Oh, lovely. Got the negative. Beautiful. Whose derivative is e to the x? Love it. Solid. And that's probably, then there's a lot of like bullshitty trig functions that it just seems a little forced. Where's that one come from? I'll just put it on. Tangent, yeah. And x. And then all the other even worse ones, secants and blah, blah, blah. That'll get us pretty far. This is enough for right now. So let's do some problems, my friend. And let's answer a burning question you've had since you first learned trig. If I take the graph of sine of x between 0 and pi, what is the area in the first hump? Everybody wonders this. And now you finally can know. So let's do it. What is that area? So that area is the integral from 0 to pi sine of x dx. Watch how this works. Take an antiderivative of sine. That's negative cosine. I'm going to show you some notation. So that's negative cos x. I'm going to put that in parentheses so that I don't forget there's that negative attached to it. I'm going to write this line. This line means evaluate at. So I read, this should be vertical. This means evaluated at. And then here I move these limits. And I would like you to use this notation so that you remember what you're doing. And I think I might have convinced you that notation is useful by now. So I take the antiderivative, I change the integral into this evaluation, and now I plug this in. So plug the upper limit in. So that's going to be negative cosine of pi minus, and I subtract off the lower limit plugged in. Check that out. And since I made you memorize the cosine graph, you might have a sense of what these values, and you may not remember it. It was a long time ago. What's cosine of pi? Cosine of 0? Yep, 1.
So it's just 2.
2. The area under this is 2 units squared. It's so beautiful. How can it be perfect? How can it be a whole number? You know, what's the question? Because I see one. I think I see one. No? You good?
Is cosine, wait, oh, negative.
Cool. Yay. Other questions? Let's leave that table up while I have some fun. Can you do me a favor, friends? Let's find all sorts of interesting areas that have been plaguing our psyches, keeping us from sleeping at night, no doubt. What is the area under e to the x between negative 1 and 0? First write it out and let's make sure. Write the integral sign for this. Use the notation and let's check that. That's the notation. I'm just getting, I'm just entertaining myself with the rest of this. That's where you need to get to.
We usually do 1 minus e to the negative.
Yes, sir. Yeah. How we doing on that? We get questions. And this is, I know that you're like, I'm not that fast yet. I just like, this is literally the first time I've heard this. That's okay.
Would it be
Yes. Oh, yes.
Yeah, would it be possible to get e minus 1 over e without simplifying e of 0 to 1?
Like, what were you thinking?
I just curious, like in other situations where you can't make the derivative or the exponent into a simpler function, is there a way to bring them together?
No, I wouldn't want to say in general.
Okay.
Yeah, not in general, but maybe today, as we look through more examples, you can like you can like call me out and go, how about that? Because it's hard to imagine, you know.
I was just gonna say, isn't that like 2/3 unit squared-ish?
It is.
Estimating-ish.
It is. It's like 1.7 over 2.7. Yeah, so 2 over 3-ish. Yeah, I like it. Other questions, friends? All right. Let me give you. We want to do more than just single functions there. Let's talk about a couple properties of the definite integral. So properties of definite integral. These are nice. These are pretty straightforward things. These are the things you probably would do anyway, just because it's like a natural thing to do these things, which are called linearity is the thing that you're going to see here. So this shows up. This shows up all over the place, and I'm going to show you in 2 steps. So first one is that if I have the definite integral of a sum, it's the sum of the definite integrals. So I can do each piece separately if I want. And that should be a plus. I don't know, that looks weird. And then 2, if I have the definite integral of a constant times some function, that's just a constant, I can bring it out in front. So these are kind of natural properties. You've been doing this with derivatives all semester long. You pull the constant out in front and then do the derivative of what's left. So it's the same idea here. Here's some not so obvious ones, and maybe you can help me with this. What do you think that would be?
1.
So what are you thinking, Adrian?
If you're taking the integral on a non-existent, if you're taking the integral on just a point,
Yes.
then the antiderivative would be, or would it be any constant?
So let's keep talking. It's all about area, right? And you can always kind of pull this back to area. What's the area of a rectangle with 0 base?
0.
That's it.
Okay.
So you're definitely thinking along the right way there. But check it out, there's literally no area there. So if the top and bottom limits are the same, it's like, don't find any area. I don't know why we wrote this, but there you go. And then, what about, well, this one might not be as obvious, so I'll just put this. If the limits are backwards, or I want to flip them, it doesn't even matter if they're backwards, but if you flip the limits, you flip the direction in which you're integrating. And so it changes the subtraction order on the delta x's, and they all become negative. That's the loose explanation. What I'm trying to say is that if you flip the order of the limits, it changes the sign of the integral. And I think that's about it for right now. But man, that gets us a lot of stuff. We can really have some fun now. Depending on your definition of fun. Let's do it. So, I'm just gonna give you some integrals to find here. Let's just start with a nice chill polynomial. And let's maybe go through this one together, because this is really the first complicated one, and you might be looking at that going, I don't know what the fuck to do. But that's cool, fair enough. So first off, it might be good to just realize that the antiderivative, this is basically this rule here, and it was kind of the case that Nino was mentioning. Derivative of a constant, C, is just Cx. Just to keep that, just to have that right in your tool belt, right? It's like this thing I'm going to use all the time. So that this antiderivative of this is 2x. So this little line right here means antideriv. Okay, so now let's do the next one. I'm going to bring the -3 down from here. What is the antiderivative of x?
X squared.
X squared with what in front? 1 over
1 over 2 plus
1 over 2. Yes.
1 over
Exactly. Yes. Yes. So check this out. Here's a good way to do this rule is, and I would write this out: increase the exponent by 1. Do that first. Divide by the new exponent. That's really what that rule is saying, right? So, and then divide, or then multiply by 1 over new exponent. That's a really great way to think of that rule and the rhythm behind it. So this exponent here is 1, so it goes to 2, and then I multiply by 1/2 out in front. Notice that the derivative of 1/2 x squared is x. Sounds like Discord is going off. Sorry, it's disturbing. What about this one? Can you just take a second? Nobody say it out loud quite yet, but everybody, what is the antiderivative of x cubed? Oh, yeah, Nina.
This is a side note.
Yeah.
Should the polynomial 2 minus 3x plus x cubed be in parentheses technically because of the dx?
It doesn't necessarily have to, so that's why, that's a great question. It could be, and it's not wrong, but these are kind of framing devices.
Okay.
So in some ways, whatever's to the left of that and to the right of that, I just take as the whole thing. Yeah, good question. 1/4 x to the 4th, love it. New exponent, divide by new exponent. Solid. Now, if you've done this before, you were in calc in high school, and you're like, plus c, that's okay, but you don't need to write that in a definite integral. That's something we'll talk about on Friday for an indefinite integral. For definite integrals, no plus c is needed, because it's just going to cancel out anyway. And then I'm going to evaluate this from 0 to 2, that's it. So I bring down that evaluation line to remind myself I'm not done. I'm going to do this. I'm going to simplify. This is 2x minus 3/2 x squared plus 1/4 x to the 4th from 0 to 2. Plug in the top. This is a common mistake. Plug in the top limit, plug in the bottom limit, and take the difference. This minus that. I don't know why, is this something that folks have a lot of trouble with? So I put in the 2, I've got 2 times 2 minus 3 times 2 squared plus 1/4 times 2 to the 4th. So now, Nina, I would probably, at this point, I would definitely use parens on this. So this is at 2, and then minus Well, you can see when I plug it into 0, it's just all dead. I hope that's not like, I don't know, I worry all the time as a teacher, like that I'm triggering people. That's something I hadn't worried about like in the past. But like recently, people are more sensitive these days. So I hope it doesn't upset anyone when I call things dead, because I do it all the time. And it might, I don't know. If it does, send me an email. You don't have to say it out loud. But it's freaking croaked in the grave, 6 feet under, choked it out. Hopefully that wasn't triggering either. And then this is 4 minus 6 plus 4 is 2. We can do this, right? We can do this. We have come a long way today. That was a hell of a push. We basically made it to the top of the mountain, and then we went back down and had a little lunch, so we're good for today. Adrian.
Is there any difference between an antiderivative and an integral, besides the fact that an integral is done on an interpole?
Yes, so I would think of it this way. An antiderivative is a necessary construction to compute an integral, but an integral doesn't have to necessarily be related to antiderivatives. You can just think of it as that process on its own. That's what I would say. Because sometimes we can't find an antiderivative, and you still have to do the integral. And so you call on the computer and summon it to do things for you. Yeah, great question. Thanks, friends. Bye. See you on Wednesday, unless you're hanging out and talking to me. Yes.
No, I'm not hanging.
Okay.
It's not that I don't like you or anything, but.
Oh, no, it's fair enough. And we're going to talk. And we're going to. You got time to talk?
Yeah.
Okay, great.
Sweet.
I was worried that I didn't. Oh, thank you. Can you stop that, please? Yeah.